Where are my slides? So I was going to do step 11, step 13, so slip weakening. So let's look at what step 13 looks like. Let's bring over our, we'll copy these over. Into our PETSI settings. So difference here, slip weakening. Here, there's a parameter to force healing once the slip rate has reached 0. Sometimes in dynamic simulations, even after the slip rate has reached a very, very small value, we don't want it to actually heal back again. So there's, additional parameters to try and solve everyone's problems in terms of both quasi-static and dynamics. Here's our parameters for the slip weakening friction. So we have a static coefficient of friction, dynamic coefficient of friction, the slip weakening parameter, and cohesion. So there's no units for the coefficient of friction, so it's 0.6, 0.4. We use a slip weakening parameter of 0.2 meters, and then cohesion of 0. And let's see, what was our, I want to look at, here's our displacement. So we're going to drive this thing with, drive the deformation with the prescribed velocity boundary conditions. So this is a little different than what we've shown previously. So we're going to put in an initial. So here's our database initial. So we're going to put an initial displacement. We're going to put in the initial compression like we did in the last problem of 1 meter. And then on the, we're going to put in a rate boundary condition that in the y displacement, we're going to go 1 centimeter per year. And on the opposite side, we're going to go minus 1 centimeter per year. So we're going to have velocity boundary conditions that are sharing, and they're just going to go at a constant velocity. Initially, we'll squish it, and that's our elastic pre-step. We squish, and then we put on velocity boundary conditions. So eventually, the faults, we'll see that initially it'll be locked. It'll then reach the threshold. It'll slip, and then it'll lock back again, and so we'll get stick-slip behavior. We're going to go, let's see, where at the top, where's my time step information? Here we are. So we're going to go 200 years, time step of 5 years. So what you'll see is that when it's locked, the fault should the nonlinear solver should converge in one iteration. When it's slipping, it's going to take a number of iterations, and so you'll see that the solve will progress very rapidly on the time steps where the fault is locked. So that I think that's what's going on here. Then it's going to take slower on the time steps when it has to do a bunch of nonlinear solves per time step. So it's cranking every 200 years. There it is. So what I'm going to do is I'm going to do a grep for nonlinear. Step 13 log. So here you can see what it did. So initially it's doing one iteration in the nonlinear solve, that's when it's stuck. Then when because we have a little bit of variation in normal tractions with the domain deforming a little more at the top and bottom and the corners, we get a few points are slipping, so it takes a few nonlinear iterations. Then we're going to get a big slip event, so it's going to take 24 iterations locked up. Then we have some additional point slipping, so it's going to take one or a few iterations. Then the whole thing's locked, so it goes down to one. Then now we're getting sort of steady state behavior of 49 iterations, a bunch of locked 49, a bunch of locked locked, and then 49 iterations. So if we load that up in ParaView, we can see what that looks like. So step 13, now I have multiple time steps. So to grab all the time steps in ParaView, I can either grab a single time step, or I can grab all of the time steps by selecting all of those that were lumped together. With HDF5, all you have to do is load up the XDMF file. So here's my domain. Let's see. We want it with edges. Let's color displacement in the Y direction. Show that. Well, let's go to the very. Oops. Go to the very end. Rescale. So at the end of our simulation, we had 2 meters of offset. You can see we're going to have slip, so let's go back to the beginning, warp by, I think 200 is reasonable in this case. In this case, at the beginning, I don't have any Y displacement, but I did have X displacement. So I'm going to slowly, so here here's our, let's see. So here's our original configuration. So here's our velocity boundary conditions kicking in. So here we had, everything was stuck. Then things started to slip a little more, stuck, slip. Now it's stuck. I need the filter to animate time. So let's see. I must have done. So it did not it's telling me the time step, but the time is not in years. I think, let's see, what did I do? What did I tell it? In the output. So in the output, I said for the domain. For the domain, I said output every 20 years and normalize the timestamp by a factor of 1. So that's why. So it thinks that ParaView with the VTK output, it doesn't have our full timestamps. It's reading the time output from the timestamp in the file name. So that's why we're getting sort of this, when I look at whereas the HDF5, we have the timestamps actually in the file. So it gives you sort of a more realistic picture of what the actual time steps are. That's why here, we're only going up to 10. 10 time steps were written. And it's reading the values of the timestamps in our output. So here, if I look at step 13, you notice they're even going, so it's even not as smart as I thought it would. I thought it would at least read the timestamp, but it's basically saying how many time steps have I written, which is sort of lame. Use another advantage of the HDF5 file is ParaView isn't very smart. That is so that didn't really. We were only by only writing out every 20 years. We didn't see a whole lot. So I'm going to import the ground surface. So here's our ground surface. We'll color by y displacement. Surface with edges. Let's also bring in the faults. So there's our fault. Let's put on the slip. Let's see. Let's normalize everything by our last values. Slip in the z direction. That's not very interesting. So there's our slip at the end. Displacement. Slip one place. Displacement y in the other place. Let's distort by a factor. Exaggerate by 200. Let's go by 500. Let's see the fault move. So here's stick on surface edges. So here we'll be able to watch, rewind it. So it still doesn't, you can see the stick slip behavior. It's pretty, I do it by hand. So there's the first stick slip. Now it's going to stick. So that gives you an idea of the stick slip behavior. If you had a bigger domain and did longer time, you could, and had a bigger drop in the coefficient of friction, you could get bigger stress drops. Any questions on this example? Yep. How would we do that? So we're going to need a spatial database for our, so what we'll do here, let's copy these. So we don't want a uniform database. We want a simple database. It still has the same label. So database, the properties, the IO handler equals, let's call it simply depth. So we'll make it a function of the spatial variation of depth. So slip weak depth dot spatial db. I don't remember how to write what a header looks like. So let's paste in what a final slip one looks like. How many values do we have? We have 4 values. The values are the values up here that we used in our uniform spatial database. Units, we have none, meters, pascals. Number of locations, let's just make it a linear variation 2, data dimension of 1, space dimension 3, 2 kilometers 3, space dimension 3. I'll just get rid of those. So let's go top and bottom. Static coefficient of friction. Assuming, what do you want? You want uniform and different dynamic coefficients of friction? Okay, different. So we'll go, 0.4. Let's make a little bigger stress drop, go down to 0.3. Then what do you want? Like 0.2 at the surface and 0.1 at the bottom? And 0 cohesion. I don't think a whole lot is going to happen with. Let's do something. Let's make it like 1.0 at the bottom. Sort of very sort of viscous type behavior. Okay. So let's see what happened. So now we're getting, we had two sort of looks like big slip events. And after our first one, we had quite a bit of additional little stuff going on, it looks like. So let's load up the fault and watch the slip rate. Or let's watch the slip. So let's look at slip. Get the side view of the faults. Fill our screen. Let's go to the end. And okay, rewind. Get our vector there. So I think it's a little, let's see. Whoops, sorry. Okay, so the problem is the color scale is up. So here's things are getting interesting here. So here was zero slip. Then the slip, so the slip started in the middle. Then there's 0.3. So we have a sort of depth dependence to our slip, but then spreads over the depth. That was sort of, here's our progressing. There was a big slip event. So let's back up a little bit or move forward, see where. So that's where we were. Then we had another big slip event. Not nearly as much to slip the depth dependence in the second event. So that second event looked like pretty much, if we look at our nonlinear solve, so after the first one, we sort of had this, it started near the surface, and then it spread, then it locked up again, and then the whole thing slipped at once, and then it locked up again. So that second event, it did it all in one time step, and looked like it looked like a little more uniform in terms of the slip. Yeah. Yes, that's why I'm sitting here with the cord already plugged in. I had 6%. Any other questions on this one? Let's see. So to automatically scale to the, no, but to have it as you rescale it, I think you can, sometimes I think it maybe used to be that way, but I don't think it's that way anymore. So I could have figured out when so I can, so say in here, let's see, where's my, let's see, when was this slip event? So here was, so time step 34, so something's going on between 33 and 34. So I think the only way I can do that is to go in here, load each of these files individually, and then subtract them. And with the HDF5, I could go in and I could subtract the two fields. I could create a separate field that was like the increment of slip. PyLith can output slip rate, so I could go in here to my step 13. Somewhere here I must ask for the fault outputs. I don't say what values I want, so I'm going to say vertex data field equals slip rate and traction. No, we don't output. We output strain, but not strain rate. Right, Charles? I think we output total strain. We don't output the rate. It would be, you could create a different cell filter that instead of just averaging over the quadrature points, average over the quadrature points and divided by the time step to get a rate. Although I'm not sure we pass in the time step information. But that is, you could do it as sort of either a separate post-processing or, that's one of the things that we hadn't thought of in terms of, we tend to sort of output sort of the state of the system. And so for the viscoelastic, you can output the viscous strain. For the elastoplastic, you can output I think, plastic strain as well. So sort of more just the basic parameters that are readily available. Slip rate, because a lot of fault constitutive models depend on slip rate. That was one of the reasons we store it internally. The velocities, the solution field, we need sort of usually have a rate. We compute the rate anyway, like the velocities for this solution, so that's an output option. So generally only, instead of creating extra fields that would increase the amount of memory, we've sort of stayed primarily with what's we already compute. And we assume that if someone wants some other field that they're going to post-process to get whatever they want, like stress invariance or something like that, we'll output the stress tensor and let someone compute those. We could create a filter that would do that internally if someone thought that the full stress tensor was, too much information in terms of, they wanted to save the stress tensor, they wanted to save some stress invariant at every single time step or something like that. 6 values over every single cell can be pretty big. So that worked. So here, let's look at the faults. So now I should have slip rates. So let's see if So I don't think, does it rescale over all of the? It used to rescale. There used to be an option somewhere in here. So here it is. Let's see. It really didn't. That.
Oh, I know. You have to do that, and then you have to go down to the update.
So I do that.
Then you did it.
That still didn't do it.
Sometimes the update. No, it's rescaled right for the first time, but then you got to play it right. No, I think it will set the scale for the highest and lowest. Is that what you want? I thought you wanted a lot of times it takes multiple hits. That sounds like kidding. Yeah, well, it is.
No, I want the lateral. I mean, it was there. So if I go back, I saw flashes of red propagate over. So part of it is the slip rate is output now in meters per second, so not meters per year, which would be a little more appropriate. So that's, I mean, that is why the scales are pretty small, but it should have been able to do a little more, you know. And so there was there was a big one. So there was my big slip rate that was nearly, let's see how uniform it was. So there's, you know, that's looking a little more like just a big slip rate event over the fault. Any other questions?